Eager space.
If you've watched my videos on nuclear rocket engines, you know that I think most of them are crazy, with the possible exclusion of nuclear thermal designs, which would definitely work but aren't very exciting. There's another approach that still uses nuclear fission, but not directly in the engine. You take a small nuclear reactor, plug it into an ion thruster, turn on the ion thruster, and you have a nuclear electric propulsion system. Nuclear electric propulsion is getting a lot of press these days. Just how promising is it? To start, we'll need to understand a little bit about rocket engines. Rocket engines work by throwing mass out of the rocket nozzle. The amount of thrust you get is equal to the amount of mass you throw out, multiplied by how fast you throw it, otherwise known as the exhaust velocity. That would typically be written using the specific impulse rather than the exhaust velocity. You want the highest possible specific impulse so that you use less mass for a given amount of thrust. Less mass devoted to propellant means more mass devoted to payload. The classic RL-10 engine is one of the most efficient chemical engines around, with a specific impulse of about 450. To get higher specific impulse, you need to run your engine hotter, but the RL-10 is already running at a temperature of about 3200 Kelvin, and you can't go much hotter than that without melting the engine. What we need is a way to accelerate our propellant atoms without using a rocket engine that is temperature limited. This is not a new idea. Konstantin Tsiolkovsky appears to have come up with it about the same time as liquid-fueled rocket pioneer Robert H. Goddard. Goddard got his approach patented way back in 1920 in a patent titled Method of and Means for Producing Electrified Jets of Gas. The concept is pretty simple. We introduce our propellant into an ion generation chamber. Electrons are introduced into the chamber through an electron gun, and the electrons collide with propellant atoms, knocking electrons off of them and leaving those atoms with fewer electrons than normal, and therefore a positive charge. We call those positive ions. Now we have a bunch of positive ions floating around in our propellant gas. If we put a plate near those ions and put a negative voltage on it, something around a few thousand volts, we will create an electrical field and the atoms will be strongly accelerated towards the negative plate and thwack into it. That might be useful for physics experiments, but it's not a very good rocket engine because it has no exhaust. What if we made some holes in the plate? The holes let some of the ions make it through and out into space, so we have a rocket engine, but the other ions are going to hit the structure of the plate and quickly damage it. What we need is a way to guide the ions so they will go through the holes. The solution is to add a second, positively charged plate, one with bigger holes. The holes are sized so the ions can still be attracted to the negative plate, but the positive plate charge ensures they only go through the holes, which are aligned with the negative plate holes. Here's a nice diagram of how it works. The positive plate is known as the screen grid, and the negative one is called the accel grid. What is actually used is a plate with hexagonal holes in it. Ion thrusters are great. Not only do they look really cool, they can accelerate their fuel atoms to very high speeds, yielding high specific impulse and very economical fuel usage. The Starlink version 2 thruster uses argon as a fuel and has a specific impulse of about 2500, or over 5 times that of the best chemical rockets. That is great. The problem is that accelerating the ions requires power. With chemical rockets, that comes from the chemical reactions between propellants, but since ion thrusters don't use chemical reactions, they need electrical power. This thruster can use 4.2 kilowatts of power, and from that power, it will generate 170 millinewtons of thrust. That's roughly equivalent to the weight of 3 AAA batteries. This low thrust has limited the use of ion thrusters, but there's one application where they dominate. That application is geosynchronous communication satellites. The target orbit is a very high orbit. The most efficient way to get there is to start with an elliptical geosynchronous transfer orbit, where the spacecraft coasts all the way out to geosynchronous orbital distance and then a rocket engine is used to circularize the orbit. That might be done with a thruster that is part of the satellite, it might be done with a dedicated kick stage, or it might be done with a rocket second stage. That's the old way of doing things, but as ion thrusters got practical, they were first adopted for station keeping, small movements to keep the satellite in the proper location, and then ultimately they were adapted to replace the chemical thrusters used to place the satellites in the proper orbit. That was the advent of the all-electric communication satellite, such as the SES-20 satellite built on the Boeing 702 SP satellite bus. All-electric is a bit of a misnomer because the ion thrusters still require a fuel. Communication satellites are uniquely suited for this application because they already have large solar panels to provide power for communications, so no additional power source is required for ion thrusters. That is, at least, if you're willing to wait 6 to 9 months for your satellite to get into the final position, following a very long spiral trajectory. The answer to that question has generally been yes, though some customers will pay for a launch vehicle that can put them closer to the target orbit so they can begin operations earlier. If we want to replace chemical rockets with electric thrusters for missions that require more thrust, we need more power. If we want to generate the same power as the RL-10, we need to figure out how much electrical power that would be. The answer is about 240 megawatts. Chemical combustion is very good at creating immense amounts of power, and the RL-10 is a second stage engine, and when getting into orbit you need a lot of thrust to get there quickly and reduce gravity losses. Once you're in orbit, you can get away with much lower thrust levels, as shown by the communication satellite example. We have a trade-off. If we want to go to Mars, we can build a small reactor that is cheap, or we can build a larger reactor that is expensive. The trade-off would seem to favor small and cheap, but if we take that route, we will never get there, or at least not in a reasonable amount of time. A big reactor will get us there quickly. Practical designs seem to be in the megawatt range, and I'm going to use 10 megawatts, with the E suffix meaning we need to have megawatts of electricity. You may be asking yourself if you can get this power from solar arrays, and the answer is yes. But that would be another video, one on solar electric propulsion. Nuclear reactions are fairly straightforward. A neutron hits a uranium-235 atom and causes it to break apart into fission fragments, 3 neutrons, and energy in the form of gamma rays. Those fission fragments may also break down themselves. Our first problem is that there's nothing electrical going on. The fission fragments have a lot of velocity, but they soon hit other atoms, and that velocity is converted to heat, as is the kinetic energy of the neutrons and the energy in the gamma rays. We have this fancy nuclear reaction thing going on, and all we get out of it is heat, the same as we would get from a campfire. The reactor's job is taking cold working fluid, whatever is used to transfer heat, and heating it up to a high temperature. That working fluid is then piped to a turbine, which extracts energy from the hot working fluid and then turns a generator to create electricity. For the turbine to work, there has to be a place for the working fluid to go after the turbine, and that is the job of the cooler. It removes heat from the working fluid to make it colder and denser. Generally speaking, the higher the inlet temperature and pressure of the turbine, and the lower the outlet temperature and pressure of the turbine, the more power you get out. The cooled working fluid then circulates back into that reactor. The cooler needs a way to get rid of the heat, and in terrestrial power plants that is done with some cooling coils in the cooler that circulate cold water, and that water is typically cooled off in one of the iconic cooling towers. What this means is that only some of the heat from the reactor goes to turning the turbine to create electricity. The rest has to be taken away by the cooling system. A typical nuclear power plant will convert about 33% of the heat energy into electricity, and the remaining 67% will be released into the environment. Space reactors need to be simple and light and are probably going to be in the 20 to 30% efficiency range. That means if we need to get 10 megawatts of electricity, we're going to have to somehow get rid of 30 megawatts of heat. It's once again a problem with heat. Noted University of Washington professor Abe Hertzberg wrote the following when discussing thermal management in space. I think it fair to state that, in many of the sketches of space industrial plants I have seen, the power system is little more than a cartoon because it lacks sufficient detail to address the problem of thermal management. Those of you who have watched my orbital data center video may remember that we needed huge radiators to get rid of a puny 250 kilowatts, and that would seem to make our problem hopeless. 30 megawatts divided by 250 kilowatts is a very big number, a radiator 120 times this size. But we aren't cooling a bunch of fairly cool servers. We're cooling a very hot nuclear reactor. It turns out that higher temperatures make things much better. Stefan and Boltzmann figured this out and came up with what is known as the Stefan-Boltzmann equation back in the late 1800s. The amount of energy a surface can radiate is equal to the emissivity of the surface, how good it is at getting rid of energy, multiplied by a constant, and multiplied by the temperature in Kelvin raised to the fourth power. It's that to the fourth power part that we really care about. If we could double the temperature from 300 Kelvin to 600 Kelvin, our radiator would emit 16 times the energy. Or, to put it another way, going from 300 Kelvin to 600 Kelvin would reduce the required radiator area by a factor of 16. That might just make this practical. Here's a nice little chart for a space reactor producing 10 megawatts of electricity at 25% efficiency. The x-axis is the temperature in Kelvin, and the vertical axis is the radiator area in square meters for that temperature. If the radiator temperature is 400 Kelvin, we will need 27,600 square meters to dissipate the energy we need to get rid of, or a square array 160 meters on each side. Doubling the temperature to 800 Kelvin reduces the area to 1,720 square meters, only 40 meters on a side. And if we could push it to 1200 Kelvin, that only requires 350 square meters, only 19 meters on a side. We clearly want a system that uses the highest practical temperatures, and that is going to require high temperature radiators. The first approach that comes to mind is a pumped loop system. A system using pumps is very simple. You have a heat exchanger to take the heat and put it into a fluid we are using, a space radiator to get rid of the heat, and a pump to keep things moving. The International Space Station uses this approach, and the Space Shuttle used this approach with radiators inside the payload doors. How would that work in our reactor scenario? Our radiators are composed of very thin tubes and probably fins to work effectively. We need a coolant that works at the temperature that we want to use. Ammonia and water are used on the International Space Station, but their maximum temperature isn't very high. Dow Chemical makes a product called Siltherm 800 that goes from 233 Kelvin all the way up to 673 Kelvin. A bit pricey at over $50 a gallon, but definitely an option. At those temperatures, we would still need over 4,000 square meters of radiator area. What we really want is higher temperatures than that, so we can make our radiators smaller. And for that, we'll need a coolant that is liquid at much higher temperatures. That takes us to the alkali metals, including sodium, potassium, cesium, and lithium. An alloy of sodium and potassium known as NaC78 has a nice low freezing point and a relatively high boiling point, but it's not as hot as we'd like it to be. These alkali metals have the small downside that they catch fire or explode when exposed to water or air. We could also use metallic salts like sodium chloride and lithium chloride. They have great boiling points, but high freezing points as well. There are two main issues when using metals or metallic salts as coolants. The first is that they freeze, or solidify, at relatively high temperatures. If you lose your hot input flow, either because you shut the reactor down or you have a fault, there's no more heat input, but the radiator will keep doing its job of radiating away heat, and the coolant will solidify in the tubes. At that point, your radiator is purely decorative, and you probably can't melt it out because the radiator is better at radiating heat away than at conducting heat through the cooling channels to melt. This may also be an issue when you're trying to start the system up. A second issue is that those thin tubes can be damaged by micrometeoroids, at which point your radiator starts venting fluid into space. Not good. Are there alternatives? NASA has a number that they call advanced concepts. The obvious solution to our radiator issue is to get rid of those troublesome tubes, which sounds like a silly idea, but in microgravity the rules are different. On the hot side, we place coolant emitters and they spray the coolant into space in the direction of the collector, and the fluid cools as it travels. The droplets have a lot of surface area, so they shed heat rapidly. This makes our radiator design small and light, which is good, and the design is known as a liquid droplet radiator. There are a number of different configurations for this design. I'm not sure how you keep the coolants from freezing on the input side if you don't have heat flow, but you might be able to make it work with a low temp coolant and be able to heat up the emitter enough to melt. The Russians have run 2 experiments of this technology, one on Mir and one on ISS. It kind of sort of worked in that they could generate the droplets and could collect them in the right location, but there's a lot of technical development to make this practical. There's also a Curie point radiator. It exploits an interesting property of some materials. When they're cold, they are highly attracted to magnets, but when they are hot, they lose much of that attraction. The temperature where it changes is known as the Curie temperature. We put a strong electromagnet right at the outside of our radiator and run a coolant pipe through the middle with a catch basin around that pipe. Take either particles or particles suspended in a liquid and spray them out into space. When they're hot, they're above the Curie point and therefore travel mostly straight. But once they cool down below the Curie point, the magnetic attraction is greater and they're captured in the catch basin. You might call this a magnetically assisted droplet radiator. One problem with droplet radiators is that they would prefer to be stable in space rather than thrusting towards a destination. There's also the moving belt radiator, where the belt flows through a heat exchanger that has hot fluid in it, absorbs heat, and then radiates that heat off into space, and the wire loop radiator and rotating disc radiator. These approaches might work, but would need a significant amount of development. Is there an option that's more likely to work? The proven approach is to use heat pipes. In a heat pipe, we have a substance that is liquid at cooler temperatures on the left of this drawing, but when we add heat, it vaporizes. The vapor travels to the other end of the heat pipe, where the heat is radiated away and the gas turns back into a liquid. There's a lot to like about this system. Each heat pipe section is independent, and therefore damage to one section doesn't compromise the whole radiator. It doesn't take any power to operate, and with good design you should be able to shut it down and restart it just by adding heat to the hot end slowly. That will melt the coolant back to liquid and eventually turn it to gas. The actual designs use a heat pipe that connects to a heat exchanger out to a finned radiator that will actually dissipate the heat. You can build heat pipes with different materials. In this design, the hottest end uses sodium, then it moves to potassium, cesium, and finally mercury. Here's what a proposed craft looks like. Note that as the temperatures get lower towards the rear of the craft, the radiators have to get bigger. Heat pipes are not surprisingly used in NASA's kilopower reactor designed to provide power on the lunar surface. Heat pipes are likely practical for getting rid of the reactor heat, but the downside is that they're heavy. That is why there's interest in alternate radiator designs, but right now heat pipes are the preferred solution. Now that we've thought about how to get 10 megawatts of electrical power, we need some thrusters that can use more energy to produce more thrust. And I've classed these all as ion thrusters, but they actually use somewhat different approaches. Going back to the Starlink thruster, we would need about 1,200 thrusters to use 10 megawatts of power. Probably too many. The X3 Hall effect thruster puts out 30 times the thrust, and we would only need 50 thrusters to use 10 megawatts of power. Better, but still too many. The MAT 100 MPD thruster is about the same at 50 thrusters, but there are designs for higher power that haven't yet been built. Could we do better? Another option is VISIMR, which isn't technically an ion thruster, but is still electrically powered. There are theoretical designs that can be high thrust, but current state of the art is a 200 kilowatt model. though it doesn't run at 200 kilowatts yet. 10 megawatts gives us 25 thrusters. 25 thrusters seems possible to me, but that's a lot of complexity and mass compared to a single chemical engine. Scaling up those thrusters brings up another issue, and, remembering what Abe Hertzberg said, it's not surprising that it has to do with heat. We already know that the reactor, turbine, and cooler are going to need to get rid of 30 megawatts of waste heat, but we also know that it's at a high temperature, and therefore the radiator area will be reasonable. The turbine drives a generator to generate the power we need, and that feeds into a power conditioning system that converts the generator power into the power the thruster needs, and that power goes to the thruster. And then finally, the thruster takes that power and uses it to accelerate the propellants out to generate thrust. Generators are fairly well understood, and good ones convert 95 to 98% of the mechanical power into electricity. That means we are losing at least 2% of 10 megawatts as heat, or 200 kilowatts. And it's a relatively cool heat, closer to the temperature electronics want than the temperature the reactor creates. How efficient are the thrusters themselves? This is a complex question, and I'm going to start with the assumption that any losses in the thruster become heat. That's not quite right, but it's close enough. In trying to figure out thruster efficiency, I started with the Wikipedia ion thruster article because it has a nice table showing input power, specific impulse, and thrust. That's very useful, as we know the thrust we get is equal to the power in watts divided by the specific impulse multiplied by 9.8. If we know the input power and the actual thrust, we can compute the efficiency. We can try that with the Starlink Generation 2 thruster, and we get an answer of 171 millinewtons, pretty much an exact match, if the thruster was 100% efficient, which it isn't. That means the input power is not actually the input power, or the thrust number is wrong. If we do the same thing with the PSP 1350 thruster, we get a calculated thrust of 92 millinewtons. Once again, a pretty much exact match. Neither of these thrusters are actually using input power. The AEPS thruster uses 13.3 kilowatts of power, and at a specific impulse of 2900, it generates 468 millinewtons of thrust. The stated thrust is 600 millinewtons, giving an efficiency of 128%. If we look at the numbers for next, the expected thrust is 168 millinewtons, and the thrust listed is 236 millinewtons, for an efficiency of 140%. Some of these thrusters are just using the output power rather than the input power, which doesn't tell us anything about their efficiency. And some of these thrusters are using numbers that clearly don't go with each other. That didn't work out. I found a 2014 presentation by OHB System, a German space system supplier who has the contract for ESA's Galileo navigation satellites. They say that the typical electric propulsion system provides a thrust efficiency of about 50%. That roughly agrees with this chart from the Defense Systems Information Analysis Center, which says 35 to 60% for Hall effect thrusters, 40 to 80% for ion thrusters, and up to 70% for VISIMR thrusters. And this slide from Ad Astra talking about their VISIMR thruster prototype, which they say they are getting a system efficiency of 60% from DC power in to jet power out. What this means is that you'll need to find some real numbers from the thruster you are going to use, but let's be generous and go with the 60% number achieved by VISIMR. That means our losses are 40% of our 10 megawatt input, or 4 megawatts. Since we're looking at radiators, we know that we need to know the temperature of those heat flows. 4 megawatts of relatively cool heat, because these thrusters use electronic components such as coils to generate them, and with VISIMR, they're superconducting coils, which have to be kept cold. Our plan is to keep our reactor operating down in this area on the right, with temperatures at 900 Kelvin or above, so that we can keep our radiator area small. But we have these other lower temperature heat loads. If we need to keep the generator at about 300 Kelvin, 27 centigrade or 80 Fahrenheit, we'll need about 430 square meters of radiator. But that's not the bad part. The bad part is the 4 megawatts that we need to get rid of from the thrusters. If the thrusters can tolerate 500 Kelvin, or 227 Celsius, 440 Fahrenheit, we can get away with 1,300 square meters. At 400 Kelvin, 2,700 square meters. And at 300 Kelvin, it's way off the top of the graph, at 8,700 square meters. Building the reactor to generate 10 megawatts of electrical power is the easy part from a thermal perspective. It's keeping the systems that use that 10 megawatts cool that is problematic. Back in 1988, NASA commissioned a study to look at big nuclear space power systems, and it includes a graph that looks very much like mine because I stole the idea from this study. The two payload curves on the left show the issue. The text says the following. It is clear that much larger areas, 2 to 10-fold, will be required for the 10 megawatt electric payloads than for the heat dissipation from the power conversion system. Payload temperatures well above 400 K are required to keep payload radiators below 5,000 meters squared. Similarly, power system radiators must be kept at temperatures of at least 800 K to 1100 K, depending on the cycle efficiency, in order to remain in a practical size range of 1,000 to 2,000 square meters. Here's a NASA design for a Mars round-trip mission. If you want the details, the paper is linked in the video description. Right out front, there are 2 reactors and 4 generators that can produce a total of 10 megawatts of power. There are 2 sets of reactor radiators with an area of 1,361 square meters, with an actual active area double that as they can use both sides. The liquid hydrogen fuel is contained in 6 tanks, each about half the size of a space shuttle external tank, containing a total of about 5,000 cubic meters of liquid hydrogen. Those are placed in the center of the craft to keep the center of gravity constant over the mission, but that unfortunately means you need a way to get the hot reactor coolant 60 meters around the hydrogen storage to the back of the radiators. That exercise is left to the engineering team to figure out. There's a crew module in the back, and there are 2 thruster modules, each containing 2 2.5 megawatt plasma thrusters, and with small radiators attached to them. This behemoth is 182 meters long and masses 560 tons at launch. That gets the crew to Mars and back home. There's a second cargo vehicle roughly half the size that carries 2 moon landers. Yes, that's what the paper says, for a rendezvous in Mars orbit. If you look at the thrusters, they have these tiny radiators attached to them. The paper tells us that their design temperature for the thrust radiators is 250 Kelvin, which means that each square meter can dissipate 220 watts, or 440 watts since they're 2-sided. The radiator they specify is 500 square meters in size, which means the radiator can dissipate 220 kilowatts. It's a 10 gigawatt system, which means the radiators can dissipate 220 divided by 10,000, or 2% of the heat coming through. I don't know how efficient their power electronics and thruster design will be, but I'm pretty sure it's not going to be 97.8% efficient. The radiators look significantly undersized. As for the generator radiator, it doesn't exist. I don't think the generator is going to be happy being next to the turbine, which is running at 1,500 degrees Kelvin. Here's the mission timing. It takes about 360 days to get to Mars orbit, 60 days for a mission, and then 329 days to get home, for about a 750-day total mission, a little over 2 years. And that may seem like a long time, but that's pretty typical for Mars missions. It takes a long time to get there. NASA has another design called Compass, which uses a hybrid propulsion system, a small 1.5 megawatt nuclear reactor running ion thrusters, and a large liquid oxygen, liquid methane chemical stage. The chemical stage is used for the parts that require a lot of delta V, getting out of Earth orbit, capturing into Mars orbit, and getting back home. I'm not going to get into the details of this proposal, but it's linked in the video description, and the design includes a lot of detail. So where does this leave us? There's a lot of activity related to nuclear electric propulsion right now. NASA has one called MARVEL, the ESA has one called Rocket Roll that I've been unable to find the final report for, and Ad Astra is working with space nukes to hook their VISIMR engine up to a small reactor as a test bed. But like nuclear thermal rocket engines, we don't have real designs actually flying. I'm hoping that somebody will build one so we can see a real-world model rather than a conceptual design. But at the current point, I'm going to call this a crazy nuclear rocket engine. If you enjoyed your video, here's your song of the day.